Hello my dear students, welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the ionic radius and its trend. In the previous lecture we have read about the atomic radius and its trend. Today's topic is ionic radius. So let's start. Ionic radii are the radius of the ions present in the crystal lattice. In the crystal lattice, that's of ionic compounds, the radius of cations and anions can be called as the ionic radii. Now, ions are formed when the neutral atom loses or gains one or more electrons. When a neutral atom loses one or more electron, it acquires a positive charge and is termed as cation. For example, we are having Na positive, K positive, Mg2 positive. So when any neutral atom loses an electron, it will acquire a positive charge and that will be called as cation. Now let's move forward. On the other hand, when a neutral atom gains one or more electron, it acquires a negative charge and is termed as an ion. For example, chlorine, the Cl negative, is a chloride ion, O2 negative, N3 negative. So when any neutral atom gains one or more electron, it acquires a negative charge and termed as an ion. Now, the effective size of these ions, that is cations and anions, is termed as ionic radius. So let's talk about the exact definition of ionic radius. It is defined as the distance between the nucleus and the outermost shell of an ion. Or we can also say that it is the distance between the nucleus and the point where nucleus exerts its influence on the electron cloud of cation or the anion is termed as the ionic radius. Now, like atomic radii, the accurate measurement of ionic radii is also not easy. However, the internuclear distance between the two oppositely charged ions, that is cations and anions, can be used to measure the radius of the one ion if the radius of other ion is known. For example, in case of NaCl crystal, the internuclear distance between the two ions is 2.76 angstroms. That is, the distance between the Na positive and Cl negative is 2.76 angstroms. Now, the radius of Na positive is 0.95 angstroms. Then how will you evaluate the radius of chloride ion, the Cl negative? So it will be evaluated as the radius of Cl negative will be equal to the internuclear distance, that's 2.76 angstrom, minus the radius of Na positive ion, that's 0.95 angstroms. So the radius of chloride ion come out to be 1.81 angstroms. So now let's talk about the next topic. The question is, the radius of cation is always smaller than the parent atom. Why so? Let's discuss about it. Let me take an example. As an example, I am taking the sodium atom and the sodium ion, that is Na positive. Now let's talk about the number of protons and the number of electrons in both of them. So first of all, what's the atomic number of sodium? The atomic number of sodium is 11. That means the number of proton in sodium will be 11 and the number of electron in sodium will be also 11. Now let's talk about the Na positive ion. The number of proton will remain same, that's 11, but Na positive has lost one electron. It's one positive charge, that's why it has lost one electron. So the number of electron in Na positive ion will be only 10. So in case of Na positive, you can see that the number of protons are greater than the number of electrons. So what does that signify? Here I am writing number of protons are greater than number of electrons. It signifies increased attraction of nucleus towards electron, because one electron has decreased towards electrons, or you can say towards rest of the electrons. That means its increase in its increase in effective nuclear charge. Hence, radius of Na positive ion will be smaller than the radius of p-n atom, that's sodium. So that means the radius of Na positive, or you can say the size of Na positive, is smaller than the size of parent atom, that's sodium. Now let me mark one more point. I'm writing here that as the positive charge increase on an ion, comma, the effective nuclear charge increases, and hence size further decreases. Let me give you one hypothetical example. It's just a hypothetical example. The size of sodium is greater than Na positive, the size of Na positive is greater than Na2 positive, and so on. So as the positive charge increase on a particular ion, size further decreases and decreases. So now I hope you got this point. As the oxidation state, or you can say the positive charge, increase on a particular ion, the effective nuclear charge will further increase, due to which the size will further decrease. Now let's move to the next part. Now the question is, the radius of an ion is always greater than the parent atom. For this, let me take an example. For example, let's talk about the chlorine atom and the chloride ion, that's Cl negative. Now let us talk about the number of protons and the number of electrons in chlorine and the chloride ion. I am writing the number of protons and I am writing the number of electrons. Now what's the atomic number of chlorine? It's 17. So the number of protons in the nucleus of chlorine will be 17, and the number of electrons surrounding that nucleus will be again 17. Now let's talk about the chloride ion, the Cl negative. The number of protons in the nucleus will remain 17, but the number of electron will increase and it will become 18. Now here you can again observe that number of protons has decreased comparatively electrons. So I'm writing number of protons are lesser than the number of electrons. So what will happen? The attractive force of the nucleus, will decrease due to the increase in electrons or we can say that nuclear charge decrease. So due to which what will happen? Due to which the size will increase. Due to which the size will increase in case of anion. In case of anion. So we can say that the radius of Cl negative is greater than that of the parent atom, that's chlorine. Or that is, the radius of Cl negative is greater than that of the parent atom, chlorine. Now again that point, one specific point which I would like to mention. I'm writing as the negative charge, as the negative charge increase on an anion, comma, the effective nuclear charge will decrease. Nuclear charge will further decrease and hence what will happen? The size will further increase. That is, let's talk about oxygen atom. That's oxygen negative, that's oxygen 2 negative. Here, as the negative oxidation state will increase, the size of that anion will also increase. In case of cation it was a decrease, but in case of anion it is increase. Now let's move to the next topic, the isoelectronic species. What do we mean by isoelectronic species? The different ions having equal number of electrons are called the isoelectronic species. And now we have to talk about the trend of size in case of isoelectronic species. For this thing, let me take an example. I'm taking an example from oxygen 2 negative, fluorine 1 negative, sodium 1 positive, and magnesium 2 positive. Now let's talk about the number of protons and electrons in each species. Now let's talk about the first of all O2 negative ion. In O2 negative, what's the atomic number of oxygen? It's 8, so the number of protons in the nucleus will be 8. How many electrons will be there? It's 8, but it's 2 negative charge, so 2 electrons have got increased, so the number of electrons will be 10 now. Now let's talk about the F negative, the fluoride ion. The atomic number of fluorine is 9, so the number of protons in nucleus will be 9. Now it's a 1 negative charge and hence 1 electron is increased. Initially the electrons were 9, due to 1 negative now the electrons will be 10. Now let's talk about the Na positive ion. How many protons are there in the nucleus? The atomic number of sodium is 11, so the number of protons in the nucleus will be 11. And how many electrons will be there around the nucleus? That's 11, but here it's acquiring the 1 positive charge, so the number of electron in case of Na positive ion will be 10 only. Now let's talk about the Mg2 positive ion. In case of Mg2 positive ion, the atomic number is 12, so the number of electrons in the nucleus will be 12, and the number of electrons, it's 12, but it's 2 positive charge, that means magnesium has lost 2 electrons, so the number of electrons will remain 10. Now here you can easily observe that these all 4 species are having equal number of electrons and hence it's a isoelectronic species. Now let's talk about the number of protons. In case of Mg2 positive, we are having the maximum number of protons. So in case of Mg2 positive, the effective nuclear charge will be maximum. Effective nuclear charge will be maximum, due to which what will happen? The size of Mg2 positive will be the least one. Now let's talk about the oxygen. Here the number of protons are 8, is the least number of protons for all these 4 species. In case of all these 4 species, the least number of proton is 8 in case of O2 negative ion. So here the effective nuclear charge will be minimum comparatively to other 3. Here effective nuclear charge will be minimum. So the size of O2 negative will be the maximum then. So in case of sodium and fluorine, the more protons is in the sodium, so the size of sodium will be lesser than that of the fluorine. So here we got the order of the size. That is, here you can easily observe that as the oxidation state increase on the number line, that's 2 negative, 1 negative, 1 positive, 2 positive, as the oxidation state increase in towards the positive state, the size of the ion will decrease because effective nuclear charge will increase. Now let's discuss about the trend of ionic radii in a particular group. Let me take an example. Let's talk about the group number 1. It's from hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Now we are talking about the ionic radii. So group number 1 always has the positive charge, that's +1, Li positive, Na positive, K positive, Rb positive, Cs positive, and the Fa positive. But as we move down the group, I'm writing, first of all, I'm writing again, as we move down the group, comma, the number of shells increase, thereby, comma, the size of the ions, the size of the cations, you can say, the size of the cations increase down the group, increase down the group, and similar to that of the atomic radii, the trend for size of the cation down the group is similar for that of the atomic radii. Now let's talk about the group number 17. And I'm talking about the group number 17 here. Group number 17 is fluorine, chlorine, bromine, iodine, and the astatine. Now the group number 17 acquires a negative charge. This F negative, Cl negative, Br negative, I negative, and At negative. And again here in this group also, as we move down the group, the size of the anion will increase because the number of shells increase down the group. Here the size of anions also increase down the group, also increase down the group due to increase in number of shells. Due to increase in number of shells. Understanding the ionic radii for a particular group was a easier task. Now let's talk about something difficult, that's trend of ionic radii in a particular period. For a period, let me take an example of period number 3. So I'm writing sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. So now let's talk about the oxidation states of all of these. Now let's talk about the sodium. Sodium acquires the +1 charge. What about the magnesium? S +2 charge. Aluminium +3 charge. Silicon +4 charge. But from phosphorus, it's -3 charge. Sulfur -2 charge. Chlorine -1, and argon, it's a 0. So here the ionic radii, the size of ionic radii will vary. Now as we are moving from left to right, from sodium to silicon, the positive oxidation state is increasing. Here the positive charge, or you can say oxidation state, the positive oxidation state is increasing, and hence size will decrease up to silicon. Now from silicon to phosphorus, just from silicon to phosphorus, size will increase as its negative oxidation state, and we all know in case of negative oxidation state, size always increase. Now from phosphorus onwards, that is from phosphorus, then sulfur, then chlorine, then size will decrease as the negative oxidation state decrease. As the negative oxidation state decrease, the effective nuclear charge will increase, and hence size will decrease. It was a bit confusing, please listen to it very carefully. Then from chlorine to argon, size will again decrease. Size will decrease because argon is neutral. Because argon is neutral. So you have to apply the concept of understanding the ionic radii in a particular periods. From sodium to silicon, the positive charge is increasing, that is from +1, then +2, then +3, then +4. As the cation, as in the case of cation, the oxidation state increase, the size decrease because nuclear charge increase, the effective nuclear charge increase. Then from silicon to phosphorus, silicon is +4 and then phosphorus is -3. It's a drastic change in oxidation state, that's from +4 to directly -3. So the size will increase because it's a negative oxidation state. In case of negative oxidation state, the effective nuclear charge decrease, and hence in case of phosphorus, the size will be perfectly larger than that of the silicon. Then from phosphorus onwards, then phosphorus is -3, then sulfur -2, then chlorine -1. The negative oxidation state is decreasing, hence effective nuclear charge will increase, and hence size will decrease. But from Cl negative to argon, the size will again largely decrease because argon is neutral in size, neutral in oxidation state. Argon is having the charge of 0. Now let's understand this thing in a periodic table. So here you can see that, here you can easily observe that. First of all, I'm talking about the group. In a particular group, let's talk about the group number 1. When we are moving down the group, as the number of shells is increasing, the size of the cations is increasing. Here you can see that the size of cation is increasing. Now let's talk about the group number 17. As we are moving down the group, the size of anion is also increasing because of increase in number of shells. In case of group number 16, the size of the anion is again increasing because of the increase in the number of shells. Okay, so that's about the groups. Now let's talk about the periods. Let me delete this thing first. Now let's talk about the periods. We have discussed about the period number 3. Here you can easily see that as we are moving from sodium to magnesium, then aluminium to silicon, the positive oxidation state is increasing. The positive oxidation state is increasing. That means the effective nuclear charge is increasing and hence size is decreasing from sodium to silicon. You can see that size got decreased due to the increase in oxidation state. Now from silicon to phosphorus, you can easily observe that from silicon to phosphorus there is a drastic increase in size because it's a change from +4 to -3. Now it's a -3, it's an anion, and hence with a negative charge, that's a 3 negative, hence the effective nuclear charge will decrease and the size will increase. Then from phosphorus onwards, phosphorus, then sulfur, then chlorine, the negative oxidation state is decreasing. It's -3, then -2, then -1. As the oxidation state is decreasing in the negative sign, so the effective nuclear charge will increase and hence size is decreasing. You can easily observe that the size is decreasing from phosphorus to chlorine. And then let's talk about the argon. It's a charge of 0. There is a drastic decrease in the size because the argon is having not any charge. So that's all for today. That's all for the topic of the ionic radii. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of the lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.